This is section 6 of the module 9 lecture, and in this case we're going to look at an example where we compare the means of two independent populations where these populations have variances that are equal, but the variances themselves are unknown. All right, this is the same example that we used in the, earlier on, where we compare the variances of two independent populations. So to remind us of this problem, here we have a drug manufacturer that is concerned about the length of time a particular drug retains its potency. So a random sample of 12 bottles are obtained from a production line, and each bottle was analyzed to determine its potency. A second random sample of 10 bottles was obtained from the production line and stored under controlled conditions for 1 year. And then potency readings were obtained on these bottles at the end of the year. So the statistics obtained for each sample are here. So the first mean, variance, and sample size correspond to the sample of fresh bottles. And then the second sample mean, variance, and standard deviation corresponds to the potency measure on the bottles that were stored over for 1 year. Now we've already shown that the two population variances are equal but are not known. So the question is, are the population means of the potencies different at a significance level of 0.05? Right, so as I mentioned before, it's always good practice to record all the information that is given in the problem, so that when it's time to populate the formulas that keep on getting bigger and bigger, then there is less likely that you will make a mistake when you enter those values into the formula. So I suggest that you do this. All right, not only that, but also in here we need to realize that we're dealing with two independent populations. Then we have the sample characteristics for both of them. We know the population variances are equal. The significance level is given at 0.05, and the objective of this problem is determine if the mean potencies are different. So with this information, we know that we're dealing with comparing the means of two independent populations that have equal variances, and the variances are not known. All right, so the first step is once you have summarized your information, then write the hypothesis, the direction of the test, and the significance level. In here, we're trying to determine if the potencies are different after 1 year of storage. So that is the alternative hypothesis, written as the mean of the newly produced drug minus the drug that has been stored for 1 year, and under the alternative hypothesis, we want to see if that is different from 0. Under the null hypothesis, we want to see if that difference is equal to 0. Clearly, this is a two-tailed test by looking at the alternative hypothesis, and the significance level is given as 0.05. The next question is what distribution to use. Well, the data in each sample are independent. These are random samples. We assume that both samples come from normal distributions. Again, it's not said anywhere, but we're making that assumption. In practice, we should demonstrate that they in fact come from normal distributions, especially since we have small sample sizes. That means less than 30. Also, the population variances are shown to be equal, but we don't know what they are, and they are going to be replaced with the pooled variance because the variances are assumed to be equal, and we demonstrated statistically they are equal. So with these conditions, then we know we're going to use a t-distribution with degrees of freedom of the sample size 1 plus the sample size 2 minus 2, which in this case is 20 degrees of freedom. All right, so once we have determined that we're going to use the t-statistic, then we know that we need to calculate the test statistic. But in this case, we need to know what is this pooled variance is. So that's the first calculation that we need to do. So we do the degrees of freedom for the first sample times the first variance, then the degrees of freedom for the second sample times the variance of the second sample, and divided by the sum of the degrees of freedom of the two samples. So here are the numbers, and those come from that summary of numbers that you already created. And so the pooled variance in this case is 0.0839. All right, so now we're going to use that number into our test statistic. So the difference of x1 bar minus x2 bar, these are the difference between the two averages that we have over here, 10.37 minus 9.83. And the difference, the mu1 minus mu2 in this case is 0, because under the null hypothesis, the assumption is that that difference is 0. So that's why there is nothing here but other than the difference between the two sample point estimates. Then in the denominator, we have the pool variance, 0.839, and the inverse of the sample size is 12 for the first sample, 10 for the second sample. If you carry out this calculation, then you find that this is 4.354. So this is the value of the test statistic. Then, now that we have the test statistic calculated, we need to determine, determine first the critical value and where the rejection regions are, because this is a two-tail test. So we divide alpha by 2 because it's a two-tail test, so that's 0.025. The degrees of freedom were already determined that those are 20. So we go into table 5, we look at the row of 20 degrees of freedom and the column of 0.025 probability, and you find that the upper critical value is 2.086. And by the symmetry of the t-distribution, then we determine that the lower value is minus 2.086. And so the null hypothesis will be rejected if the t observed value is smaller than minus 2.086 or if it is larger than 2.086. If we decide to go with the p-value approach, then we take the t observed, the value of the test statistic that we calculate it, and then we go into table 5 and try to see where this value is on the row of 20 degrees of freedom. And you see that the largest t-value is 3.552, and that corresponds to probability of 0.001 to the right. So 4.354 is larger than that. But before we do that, we know this is a two-sided test, so the p-value is 2 times the probability to the right. So will be 2 times 0.001. So the p-value is between then 2 times 0.001 or 0.002 and 0, because 4.354 is to the right of 3.552. So it's going to be a probability smaller than 0.002. And since we don't know what's smaller than that other than 0, then we say that the p-value is between 0.002 and 0. If you want to calculate the exact p-value, then you can use this formula in Excel, and you see that the exact p-value is 0.0000308. All right, so now we know the rejection region, and we know that the p-value is between 0.002 and 0. And if you have access to Excel, then you will know that the exact p-value is 0.00308. All right, so now we make a decision. So the t observed, 4.354, is larger than the upper critical value of 2.086. That means that the t observed is in the rejection region. Equivalently, the p-value is smaller than alpha 0.05. So these two conditions tell us that we should reject the null hypothesis that the mean potency of the drugs freshly produced and after a year of storage are not equal. So the interpretation of the decision, formally, we say that at the 0.05 significance level, the population average potency of the drug immediately after its manufacture is not the same as the population mean potency of the same drug after it has been stored under controlled conditions for 1 year. So again, the manufacturer said, well, great, I know they're different, but is it bigger, smaller? Where are they? We don't know. We only know that they're different. So this is where the confidence interval becomes very useful, because right now we just know that the difference is not 0. That means there is a difference between the two means, but we don't know what that difference is. So then what we do, we proceed to calculate the 95% confidence interval for the difference in potency of these two, for the drug freshly produced and after 1 year of production. So for the 95% confidence interval, we use an alpha of 0.05 and divided by 2 because we want the two limits of the confidence interval limit. So we go into table 5, we look at the row for 20 degrees of freedom and the column for a probability of 0.025, and we find that the T alpha over 2 is 2.086. So now we have the difference in means. We know the sample means for each sample. We know now the T value. We already found it. We already calculated the pool variance. And the sum of the inverse of the sample sizes is 0.183. So calculating this term and subtracting it from that difference gives you a lower confidence interval limit of 0.2813. And doing the same operation, but now adding this quantity to this difference, then the upper confidence interval limit is 0.7987. So now that we have the confidence interval limits, now we can interpret the confidence interval. So we say there is a 95% confidence that the difference in potency mu of the new drug minus the mean of the drug after 1 year of storage is between 0.2813 and 0.7987. Well, that means that you notice those two numbers are positive. So the difference between the two averages is positive, which means the potency when they are newly produced is higher than the potency after 1 year of storage, because the results under the confidence interval, both numbers are positive. So then we can say that the difference between the means is positive, implying that the mean of the mean potency after production is higher than the potency after 1 year. So we can say that the average potency of the drug after being stored for 1 year decreases between 0.2813 and 0.07987 units compared to the average potency of the recently produced drug. All right, so now again, you need to be very careful in how you interpret this confidence interval. So this is a difference, and if the confidence interval shows you the limits being positive, then you know that the first mean is larger than the second mean. And you can use that fact to explain what this confidence interval actually is telling you about the difference of the two means. And I would expect you in an exam not only to give me the first statement, but to proceed and explain what that difference represents in practical terms. All right, so this is one example of how you can compare the means of two independent populations with equal variances but unknown. So the variances are unknown. And in the homework problem on Wiley Plus, I assign you I think 2 problems like this, so you'll be able to practice this. And my suggestion is that you write down your solution. So start getting into the habit of documenting your solutions so that you're ready for the exam. And not only that, Wiley Plus does not ask you to interpret the results. Please, when you write out the solution to the homework problems, write out the conclusion so you get into the habit of interpreting the results of your analysis. All right, I will stop here, and this is all that we will cover this week. For next week, we'll continue with Module 9.